Hello class, this is Tim Tomlanovich, and we are going over Learning Plan 3, Determine Equilibrium Reactions of Coplanar Force Systems. Okay. Let's see. All right, so our learning objectives today will summarize the concept of static equilibrium, articulate the difference between reaction types, construct free body diagrams, calculate the reactions of concurrent forces. Remember what a concurrent force is remember the lines of action intersect at a common point. Okay? Calculate the reactions of parallel force systems. So those are forces that are parallel, they don't intersect. And calculate the reactions of non-concurrent force systems. Basically, the forces aren't parallel or concurrent. Okay? All right. Again, I have a lecture, LP3, lecture sheet attached in Blackboard, so you can fill that out as you're going through this. Key points that I want you to get out of this lesson. Okay, so just to review, negative forces and positive forces. So, all right, so we have black, so here are, we look right here. So our X, we have a positive X and a positive Y, up and to the right. Here we have a negative X and a positive Y. Here we have a negative X and a negative Y, and in quadrant 4, we have a positive X and a negative Y. Here, so just recall, just think of the XY axis, which ones are positive. Because why do I need to know that? Because remember, we're the 4 components of a force. We have magnitude, okay, that's the value, kips, kilonewtons. We have line of action. Now that's the angle of measured from the x-axis, line of action. Okay. What else do we have? So we got 1, line of action. Okay. We have the sense. Remember, that's the arrowhead. That's how we determine it. Right here, arrowhead, that's how we determine if it's negative, positive. Okay. And then the last one is, what do we have? Magnitude, line of action, and then we have point of application. And these 4 parts of a force vector will come into play as we do this next lesson plan. Okay? All right, so I got it. Okay, so what are the 3 equations of equilibrium? So static equilibrium, basically it's not moving. Okay? Yes, the Earth is moving, but static equilibrium, that means nothing is moving. So the sum of the forces in the x direction are 0, sum of the forces in the y direction is 0, and the sum of the moments about any point is also 0. So remember, what is sum of the moments? A moment is, number is a force times a perpendicular distance, right? And then our counterclockwise is positive moment, and clockwise is a negative moment. Okay? So if I'm pushing, let's say you're pushing a shopping cart down the aisle, okay, that's a force in the x direction, all right? So for it to stop, we got to have a force resisting back, going back in the other direction. Okay? All right, so this, remember, these are the 3 equations you'll need to remember. So for things to be in equilibrium, sum of the forces in the x, sum of the forces in y have to equal 0, and the sum of the moments about any point have to equal 0. Nothing is moving. That's how we do a lot of static equations. Okay, so let's talk about free body diagrams. Okay, so if we look at this weight being hung by a rope, okay, so if I look at the rope itself, ropes and cables can only support tension. Would you agree? How do I know this rope is in tension? Okay, because if you look, the weight right here is pulling it down, right? And then it's being stretched, right? So, see, my senses, my arrowheads are opposite direction. The magnitudes, F are the same, and my line of action has not changed. So that rope is in tension. So that's what, okay. So if I look here, this is what the free body diagram of the rope looks like. So this point right here, oops, let me go to here, this point right here, the point of application is right there. The point of application is right there. It's being stretched, right? Okay. Now if I look at the weight, right, that weight, this eye connection right here wants to be pulled out of the weight, and the weight is pulling down. Okay. All right. So I want you to look at, I'm going to erase this again here. Okay. I want you to look at this to this. Those are connected at the same point, which is right there. So if I go from the rope to the weight, the senses are opposite. The line of actions are the same, the magnitudes are the same. So depending how I'm looking at it is how the free body diagram works. Okay. So what we do, we isolate the members and we determine the forces that are in each member, and we calculate, use the three equations of equilibrium to calculate the forces, unknown forces. Okay. So going over that. So stroke eraser. Oops. All right, segment. Let's do segment eraser. That works. All right. So what I'm gonna do is I'm gonna draw this free body diagram. Okay. So I have my weight here. Okay, that's this weight right there, and then I have this force, right? That I wants to be pulled out of the rope. Okay. Now I switch to my rope. Okay. Now I switch to the ceiling. Okay. What do you notice what happens? From the weight to the rope, my senses change. From the rope to the eye, my senses change because this eye hook wants to be ripped out of the ceiling. Okay. All right. So let's look at this. So these ropes. So this is a point of common concurrency right here. Okay. You notice these ropes are in tension, right? Hence, we assume we're pointing away from the point of application, or they call that a node. Okay. So that's a point. So the trick to these free body diagrams, can you find a point of common concurrency? Yes, right there. Boom. Here it is. Okay. Then we can just draw a straight line. Okay. Right. Yeah. Straight line. That is representing this. Okay. Then we assume senses. Sense of the arrowhead. Okay. So we know ropes can only be in tension, so it doesn't matter. We can just assume, and life will be good. And then we solve the equation. So that's the free body diagram of that guy. All right. So, okay. Let's look. I'm just going to make this thinner. Okay. So if I look at this house here, the wall, that is the free body diagram of that guy. Okay. So if I look here, F1 plus F2 plus F3, those forces are acting on the wall. So the weight of this truss, which is this, right? Because I'm going from the truss to the wall, the green equals the red. The green equals red, but they're this opposite sense. Okay? All right? So if I go to this guy, so if you look here, here's the cable. Okay? and it's holding on to the steel beam. Find a point of common concurrency, which is where? Right there. Okay, which is right here. So I know I have cable CA here, CA there, CB here, CB here, and then the weight of the girder, right? Because remember, there's a weight there from physics. This pulls down. So equal and opposite. So by making a free body diagram, I can now solve the forces, the tension in these cables CA and CB by making this free body diagram. Okay. So now if I look at this one over here, so I thought this, so I have the wall, so you have a force vector, right? And then I have beam A is sitting on this wall, beam B is sitting on the wall, okay? So now I can solve by knowing the force of beam B and beam A, it's kind of treated as a point load onto this girder here. I can use static equilibrium, three equations of equilibrium to solve for the force on the wall here and the force on the wall here. Okay, that's why we do free body diagrams. Okay, so I recommend, see this little website down here? I recommend you click on that. This does a really nice job of showing how to create free body diagrams. So right here, I won't click on it because then it'll screw me all up. But click on that website. Okay. Now, if I look at this guy, here's a crane, right? Weight 1, weight 2, weight 3, weight 1, weight 2, weight 3. So the senses are down, right? Because gravity pulls weight 1 down, weight 2 down, and weight 3 down. Okay. And then the tension in the cable, see, tension, opposite sense. T equals W1 plus W2 plus W3. This is called a collinear force. The lines of action are the same. So by doing this, making a free body diagram, we're allowed to solve the three equations of equilibrium. Okay, some examples. All right, let's talk about reactions. Okay, so I want you to look right here. Flexible cable, rope, chain, or wire. Those can only be in tension. So when they are attached to an object, look at the sense. The sense is pulling away, right? Because it has to hold it up. Okay? When you say reactions, there's only one there. Okay? We have a roller. This is a roller. It looks like you're on a skating rink. So when I look at this, you think about it this way. If I push, if that's a marble, and I push this way, is it free to move? Is there any forces, is the force being resisted moving horizontally? The answer is no. It can freely move, so there's no resistance, right? However, if I push down, right, because this is right here, you see we get this reaction right there. See, so that is the wall or something pushing back to keep it still, but it's free to move horizontally. So there's one vertical reaction. Okay, so a roller, it's free to move horizontally, but it's not free to move up or down, and it's also free to rotate. Okay, so there's one reaction for that guy. Now, so we have friction. You learned that in physics. So we'll go on to the pinned hinge. Right here, this is a pin. It looks like a little triangle. Picture a nail going through it. Picture it as a teeter-totter. Now, if I put a horizontal force on there, is that nail holding that beam from moving horizontally? Yes. If I put a force up or down, is that beam being held from moving vertically? Yes. However, is it free to rotate? Yes, it's kind of like a teeter-totter. So there's no resisting force to keep it from rotating. So that's why I don't have a moment force here. Just like this one here, this roller, right? It's free to move horizontally. It's like sitting on a bed full of marbles. There's no horizontal reaction. Action is kind of like a support condition. So what we do is we simulate these connections at a wall, street, floor, flagpole, ground, connection, steel structure. We have to idealize the connections so we can make this problem statistically solvable, because we have three equations of equilibrium, so we can only have three unknowns at one time. Okay? All right, so now if I looked at a fixed condition, kind of like a diving board, okay? If I look at this, this thing is not free to move horizontally, vertically, or if I try to stand on the end here, it wants to bend it down. So there's a resisting moment, a reaction moment to keep it from bending down. So I have three reactions, okay? So you need to understand this. So when you see a little triangle or a little thing, or even a little triangle with wheels underneath it, like a roller skate, that is a pin reaction, or I'm sorry, not wheels. It's a pin reaction. We have two reactions. There's a horizontal force and a vertical force. If I have a roller, okay, now this one could be a triangle with roller skates. I only have one vertical reaction. Now the sense, we can assume the sense. We don't know which way the sense is. We can assume it's going to the left or to the right or up or down on this one, okay? This one we can assume it's going up, or we can assume it's going down. Two reactions. And then there's the fixed one. There's three reactions, okay? So it's important that you understand that. So that's where it's the beam or object is being supported. So this is, we need to do this to solve the three equations of equilibrium, okay? So again, we want to understand the roller has one reaction vertical, the pin reaction, right? Knife edge, it's rough surface, right? It's free to rotate, but it has a horizontal force and a vertical reaction force, okay? So you notice, this is another thing I want to, you notice this says R. We want to put R in front of that. That stands for reaction, okay? So you don't get those confused with normal forces sitting on your beam. So that'll make sense when we start, okay? All right, we ready for an example? Okay. Example one. All right. Okay, so we want to create a free body diagram of this, okay? So I'm going to use green. All right, so if I look here, I have a roller. This is, point B is a roller. So if I look here, I know it has a vertical reaction. So I'm going to make this a little thicker here, just so I don't have to. Oops. This side a little thicker here. All right. Okay, the reaction at point B in the y direction. Look at my sense, okay? This one is a pin. Point A is a pin. I have the reaction at point A in the y direction. These are subscripts. And then I have the reaction at point A in the x direction. Again, I am assuming the senses at this point. The math will figure out if my senses are correct. Okay? All right, so and then this guy, we have PY and we have PX, and we have a length L. So now that is the complete free body diagram. That's some point load on this beam. Now this reaction at point A in a y direction, that could be a wall underneath these, you know, point A and point B, and that's the load from the beam transferring down onto the walls, okay? So now we're able to use the three equations of equilibrium, the sum of the forces in the x, and the sum of the forces in the y, and the sum of the moments about any point will equal 0, okay? All right, so that's how we create that free body graph. All right, example 2. This is problem 4.1 of your book. All right, so I need to solve all the forces in here. So I have a point load at P1 at a distance A, a point load P2 at a distance B, okay, and this is a pin. So at the pin in B, I know I'm going to have two reactions. Reaction at point B in the Y direction, okay, the reaction at point B in the X direction, okay. Now I have a cable, because this is free to rotate. Number of pin is free to rotate. So if I cut this cable, this beam's just going to flop down. So to keep this beam from staying straight, I know I have a cable force here. Okay, tension C for cable. All right, so now sum of the forces in the X, sum of the forces in the Y, and do moments. I can solve for TC, the tension in the cable, RBY, and RBX. So that's how I create that free body diagram. Okay. All right, so that's problem 4.1. Problem 4.2. All right, so remember, okay, so you want to pick the object that provides you with the most information, okay? Find points of common concurrency. So this is a pin. So we have the reaction at point A in the Y direction, okay? We have reaction at point A in the X direction, because that's a pin. All right, now we have this cable. So we have this force here, right? It wants to pull this object going this way, right? So that means, because if I look where my pin is, it's connected to this L shape here. It's not over here, okay? All right. So this is my T, tension and cable. So then what I would do is, to make life easier, I would go TX, and then I would go TY. So now everything's in X and Y. Now I can sum the forces in the X, sum the forces in the Y, take a moment about a point, and then I can solve for T in this cable. All right. So if I just wanted, so if I do this, if I took a cable and just cut this, and I wanted to look at the free body diagram of this cable, this was what it looked like. Here's my point of application. Here's my sense. My line of action doesn't change, but it's opposite. The senses are opposite from when I go from the ground connection to the ground to the connection to the structure. Okay? All right. So now if I wanted to just cut a little piece out from here to here, now, because see, this point of application called no is attached to the structure and attached to the ground. Now, if I look at the cable, you say, well, that looks like it's in compression. No. Okay, now if I cut this piece of cable out here, which is right there, okay, if I draw my free body diagram, okay, if I look at this sense to this sense, aren't they opposite? And if I look at this sense to this sense, those are opposite. So see, when I keep switching over is when the senses change. And this will become more evident and clear as I move on. All right, so let's look at this guy. Okay. All right, so we have a pin here. So we have the reaction at Y. Okay. We have the reaction in X direction. So there's no point here. So call it point A. See, this is point B. Call that point A. So we want to put a subscript A there. Okay. All right. We have a weight here. So that's pulling down, right? And then we have this cable here. Okay. So again, this cable's at an angle. So we can do this. We can do TY, TX. Okay, because this big cable here is T, right? Okay, now if I look at the wall, if I go to the wall, it's this way. Okay, so if I wanted to solve, so I go to point B right here. Okay, that's this boom right here. Okay, so I can make a concurrent force system here. Tx, Ty, and then I also have my W, right? And then I know this will be 30 degrees. Okay, by knowing my weight, okay, right? So I'm just kind of pretending I'm cutting that. That's my free body diagram. I can find T by using the three equations of equilibrium by this free body diagram. See what I did? Is basically I cut this off the wall and pulled it apart. Okay, so now I can find T, the big T, by breaking some of the forces in the Y, some of the forces in the X, take them, okay? And then some of the moments go to point. And I can solve for T by knowing W, by what I just did there. So you guys find a point of common concurrency, which is right there at point B. But if I'm just looking here, okay, once I know this, if I'm just looking here, I'm just only seeing this, but I don't see any of this on the free body diagram. So I need to know this information before I can find this information. Okay, that's that guy. All right, we got a ladder here. Free body diagram. So we have a pin here, right? At point A. Okay. We have the reaction at point A in Y direction. We have the reaction point A in the X direction. Okay, we have a force. So this ladder is leaning up against the wall here. Wouldn't you say that it looks kind of like a roller? Okay, does the wall have to push back to hold it? Right? Reaction at point B in the X direction. Always this ladder would move, right? Then this is a person standing on it, and then we have the weight of the ladder. Okay? All right, so one thing I forgot is I didn't add the weights of the members. Sometimes we assume it's there, the weight of the ladder, weight of the members, okay? If it's not given, don't worry about it. But in reality, everything has a weight, right? So we got to add the weight of the structure. So, and the ladder, right? So we have the weight of the person plus the weight of the ladder, okay? These are negative forces because they're pointing down, plus the reaction at point Y has to equal 0 to make this thing static. Now the X, I have RAX minus RBY, because this is a negative force, because I'm looking at the sense here, will equal 0. And then I take the moments to finish up, to find. Okay? So that's the free body diagram for that guy. All right. So here's, they didn't give this in the book, so I wanted to make sure you understood, okay, is a fixed connection. This is a fixed connection. So if I look right here, we have our Y, right? It can't move down, correct? Right? We have our X, okay? And then, okay, this elephant is causing the diving board to go down like this, right? So there's a moment, the reaction moment, okay, at point, okay? So we have an opposite reaction moment keeping this diving board from pulling onto the ground, okay? Again, we can assume the sense and assume the rotation. So that's a free body diagram of a fixed connection, they call it. All right. Okay, so here's, whew. All right, so now what do? We have this point load here. Okay, so we want to do a free body diagram of this guy. So the first thing what you want to do, see this? We want to convert this into a point load. So we know this is a rectangle. So it's length times height. W is the height, that would be like pounds per foot or kilonewtons per meter. It's the area of a rectangle, and we know in the middle of a rectangle, the centroid is halfway, L1 over 2. So we get W times L1 will equal that point load, and the distance from here to here, because we need to know that, is L1 divided by 2. Okay? And then this is a triangle. Okay? So it is a pin connection. So we have the reaction at point A in the y direction. We have the reaction at point A in the x direction. And then we have, this is a roller, so we have the reaction at point B in the y direction. Okay? So if you look at my reactions here, I have 3 equations of equilibrium, x, y, right? Or 3 equations of equilibrium. Sum of the forces in the x, sum of the forces in the y, sum of the moments have to equal 0. All right? That's 3 equations. I can have a maximum of 3 unknowns to solve these equations. Okay? So obviously, so that's why I only have 3 reactions here. So this is why we have to assume one end is pin, one end is a roller. Even though in reality, we know there's not a marble sitting on top of that wall there. That beam is actually nailed to the top of the wall. But we simulate it as a roller to make this solvable so we can figure out forces. Okay? So, all right. All right, so how do we solve these? Oh, I made a step process for you. So basically from here on in, it's pretty much going to be the same. Oh, excuse me. First, we want to draw a free body diagram. Then we want to make sure our forces and all our angled forces are in x and y components, or they call them number rectangular components. So then what you do, so these 2 steps will always be the same. Now the next step 3, sum the forces in the x direction. Always start with this one. Even though if it's 0, there's no horizontal force, still start with the sum of the forces in the x direction, sum of the forces, then go to the sum of the forces in the y direction. Then if you need the 3rd equation, you go to the sum of the moments about any point will equal 0. Okay? And you solve as many as you can. Okay? So so concurrent forces will only need the first 2. Non-concurrent forces or parallel forces will need all 3. And then what you do as you solve these 3 equations, you can only solve so many. You'll have unknown variables. And what you do is you move to the next equation, and then you solve by substitution. Okay? This is important right here. This is where you're going to get hung up right here. Right here. Imperative to keep negative answers while substituting to solve for other variables. Negative answers only indicate you assumed the wrong sense. What's the sense? It's the arrowhead in step 1. Okay? Don't worry about it. The math will work itself out. Okay? So basically what I'm saying is when you substitute in, do not change your free body diagram until you get all your variables solved, and then you can switch your free body diagram, correct it, and then you check for equilibrium, because then everything should equal 0. So if you have a wrong sense, okay, you did something wrong. You can go back and change it. Okay, so it's important you change your free body diagram. All right, so step 10, 11, and 12 are critical. This will give you a self-check that I did this problem correctly. Okay, all right, we ready for an example? I'm going to pause for a second here. Okay, so example 1. I hope you can hear me because I don't have my headset plugged in. Oh, we'll find out. Okay. Example 1. Basically, I want to solve the reaction, so I need to know how to design these bolts here. Okay? So we know, I'm going to call this point A. Here's my point of application right there. Okay? We have the reaction at point Y. Oops. We have the reaction at point A in the Y direction. We have the reaction at point A in the X direction, okay? And then we have the moment about point A, okay? Free body diagram, step 1, okay? All right, okay. Step 1 is done. All right, so now I go through the equations. Sum of the forces in the X direction has to equal 0. Well, okay, so we have our AX. It's positive because I'm pointing to the right. Look at my sense. Do I have any other X forces? No. So that has to equal 0. So guess what? RAX equals 0. That makes sense. Even though you know it's 0, put it there. Okay? Next equation. Sum of the forces in the Y has to equal 0. Okay, so we have the reaction at point A in the Y direction. Okay, that's pointing up, right? My sense is pointing up, so it's positive. Then I have my little weight here, 1,000 newtons. This elephant weighs, and that's a point load right there. Okay, so that completes my free body diagram. Minus, sense is pointing down, right? Minus 1,000 newtons equals 0. So now I know the reaction at point A in the Y directions. I solve it, I slide that over, equals 1,000 newtons. So equals 1,000 newtons. Reaction at point 0 is 0. Okay. Now, third equation, sum of the moments about point A has to equal 0. So MA is what? It's going positive. So M, the moment at point A, okay, and then this moment created from the elephant from here to here, so it's going clockwise, so it's a negative, minus 1,000 newtons times a distance of 4 meters, right? Perpendicular distance has to equal 0. So now I know my moment equals 4,000 Newton meters. Okay, there's my 3 equations. All right, I ended up with positive answer, positive answer, positive answer. I assume my senses correctly. I do not have to change my free body diagram. Okay, I didn't have to do any substitution. Okay, so now I want to check, so I'm not going to do it, but now what you would do, and there will be times where we have to change this, what we would do is we would check equilibrium, but this one here is simple, so I'm not going to do it, but I will do it on a future one. Okay, so on basically these bolts sitting right here, I have to resist 4,000 Newton meters of overturning moment. I have to resist this block here has to resist a vertical force of 1,000 newtons. Okay, and there's no horizontal forces. So that's first equilibrium example. Number 2. All right, so I may have to add some pages here. These problems are going to get longer. All right, free body diagram. Find a point of common concurrency. What do we have? Okay, right here, point K. So I have this, my weight of 500 pounds. Okay, I know this is a cable. So, okay, this is what? K, let's see here. We got this. Okay. All right. So I need to find, let's see, I'm going to call this, let's call this point A. Let's call this point B. So I'm going to call this TA. I'm going to call this TB. Okay, we know it's at a 45-degree angle. Okay, that's my free body diagram. See, I'm just making up variables. All right, so step 2, everything in X and Y. Okay, so this is Tx, this is Ty. Okay, so I gotta put the little subscript TB, TB. Okay, all right, this guy, same thing. So these pointing applications are all at the same spot. I'm just moving them for clarity. So this is TAY, this is TAX. All right, so I can only have 3 variables. 1, 2, 3, 4. So how do I do that? So what you need to do is get these in forms of 1 variable. So I need to convert this TB and TA in the forms of X, of just in variables of T, I'm sorry. All right, okay, X and Y. So TX, TBX. Okay, TBX equals. Okay, so is the cosine, right? Because that's the adjacent side of my right triangle. Cosine of 45 degrees times TB, right? The hypotenuse is my TB. TBY equals opposite sine of 45 degrees times TB. Okay? All right, so got my calculator. We'll solve that. All right, cosine of 45. So that's 0.707. 0.707 TB. So the sine of 45, the cosine of 45 is the same. Okay, 1 variable. All right, we want right here, TB, we want it in the form of the actual of the hypotenuse of it, so we don't have too many variables. Okay, so let's solve TA. TAX equals cosine of 30 degrees times my hypotenuse, which is TA, and then TAY equals the sine of 30 degrees times TA. Okay? All right, so cosine of 30. So that's 0.866. 866 TA. Okay, sine of 30 is 0.5. 0.500 TA. All right, so this is in X and Y. Okay, so 1, free body diagram. 2, get everything in X and Y. 3, we start solving equations of equilibrium. Okay, so let me make that a little darker. Okay, so I'm going to probably add a page here. All right, let me just link page here, just so I have room to write. So let me take that off. Let's cut this out of here. All right, so let's go back to here. Okay, all right, so sum of the forces in the x direction. X direction has to equal 0. All right, so I have TBX. It's negative, right? So minus, so let me write this clear. Negative 0.707 TB, okay, right? Negative here, TBX. That's why free body diagrams are very important so you can see what you're doing. Then we have TAX plus, that's positive, plus 0.866 TA equals 0. Okay? So I can't solve that, can I? But I can reduce this. I'm going to move this to the other side of the equation. So 0.866 TA equals 0.707 TB. I can't solve that. So now I move to the next equation, which is sum of the forces in the y direction. So now I'm going to go to the next page. I'll go back and forth. Sum of the forces in the y direction have to equal 0. Okay? All right. So I have TBY, which is 0.707 TB, plus TAY, right, which is 0.50 TA, minus W will have to equal 0. So TBY. So 0.707 TB plus, here's TA. TA, here's this guy, that's positive, it's pointing up. 0.5 plus 0.500 TA minus 500. Right, is that how much that thing weighs? So I'm looking at this guy, this vector right here, 500 pounds equals 0. Okay, I still can't solve that, can I? All right, but I can reduce it. 0.707 TB plus 0.500 TA equals, I'm moving the 500 on the other side of the equation. Subtract both, add both sides, add 500 to both sides of the equation, the 500 goes away. All right, so can I use a moment equation? You cannot. Reason why? Because all the lines of action, right, they all go through a point of common concurrency, and the line of action goes through the point of rotation. That means my moment, I don't have any moments. So how do I solve this? This is applicable to concurrent forces. So how do I solve this? So basically, I solve simultaneous equations. So what I do is I solve for TA, okay, and then I substitute it back into another equation, okay? So I'm going to solve the sum of the forces in the x direction using for TA, okay? All right, so let me label the steps here. So I got this, so you know, this, so you can 2, 3. They're not the same steps ordered in my order of steps listed in how do you calculate these. All right, 6. Solving, going to solve this equation for TA. So I'm going to rewrite that equation. 0.866 TA equals 0.707 TB. So how do I get rid of this? So I divide both sides by 0.866 divided by 0.866. Then I get TA equals, TA equals 0.707 divided by 0.866 equals 0.816. TA equals 0.816 TB. So I can divide these out because they're common variables, right? They're numbers, okay? All right, so now what I'm going to do is, I know TA equals 0.816 TB. So I'm going to substitute this into this equation, into my sum of the forces in the Y equation. Okay, so I know TA equals that. So 0.707 TB, okay, plus 0.500. So TA now equals 0.816 times TB, okay, equals 500. Okay, so now if I solve this, 0.707 TB plus, okay, so I use the distribution property, right? 0.5 times 0.816, okay, and then the TB follows after it. So 0.5 times 0.816 equals 0.48, 0.408 TB equals 500. So step 5 continued. So now I can add these together. 0.707, we can add like variables, plus 0.408. So we get 1.115 TB equals 500, and divided by 1.115 to solve for TB, okay, comma, 500 divided by 1.115 is 448.4. So TB equals 448.4 pounds. See, I already solved that. I don't have to bring it back into, okay? I already brought it back. So that's TB. Oops. So let me go back to TB. So I solved for TB. I didn't solve for TBY or TBX. See why you need to have it in terms of TB? Because then I solve for it. If I have TBX, TBY, I have too many variables. Okay, now that I know step 6, I can actually substitute that. Okay, I can substitute that into, I can substitute this into this guy right there, or I can substitute it into this guy. Either one, you should all get the same answer. Okay, so TA equals 0.816 of TB, and I know TB is 448.4 pounds. Okay, so 0.816 times 448.4, that's 39 point, whoops, that's not right. 0.816 times 448.4, 365.9. Don't forget your units. And this equals TA. Okay? So if I go back to here, I needed to find the tension in cable TB and the tension in cable TA. So I didn't identify that. I forgot my textbook, but I know that's what they're trying to find. Okay? All right? So I solved these. Okay? Now what you want to do is you want to check, okay, I have positive answers, right? So I do not have to correct my free body diagram. Correcting free body diagram means I have to change my sense around. I got to reverse it. Okay, so I'm good. I got positive answers. I'm good. So now what I want to do is check equilibrium. All right, so now what I'm going to do is I need to convert it back into, I need to convert everything back into X and Y. Okay, so TB was 448.4, 448.4 times 0.707, that equals 317.0. Okay, same thing. So my X and Y equals 317.0. Okay, TA, okay, my X direction, so cosine of 30 times, let's see, TA was 365.9. Or I'm sorry, let's just go 0.866 times 365.9. That's 316.9. Okay, and then 0.5 times 365.9, 183.0. Okay, the more decimal places you are, the more answers the closer my answers will be to 0. All right, so I just converted everything into X and Y. Now, step 7, check equilibrium. Sum of the forces in the X has to equal 0. All right, so TB is a negative minus 317.0, okay, plus TAX is 316.9. But those are my only two X's, plus 316.9 approximately equals 0. Because of rounding, I'm good. Sum of the forces in the Y direction has to equal 0. Okay, so I have TBY. TBY is 317.0. It's pointing up. Plus TAY. TAY is 183.0. Minus the 500-pound weight. And that should approximately equal 0. And let's hope it is. 317 plus 183 exactly equals 0. So I know I did my numbers right. So there is the tension in my cable. So I just solved this guy. Holy moly, huh? All right. Example 3. Okay. Step 1. Free body diagram. Okay. All right. So this is a pin. This is our reaction at point A in the Y direction. I'm assuming my senses are at point A in the X direction. This is a roller. This is R at point B in the Y direction. Okay? All right. So, step 1, free body diagram. Okay? RAX, RAY, RBY. Step 2, turn all forces into X and Y and turn all point loads or distributed loads into point loads. So, I got to turn this guy into a point load. So we know it's the height of this rectangular is 600 pounds per foot times 12. So if I take 600 times 12, I get 7,200 pounds. 600 times 12 equals 7,200 pounds. Okay, and we know that's in the middle, so we know it's the distance from here to here is 6 feet. Okay? All right. Step 1. Sum of the forces in the x direction equals 0. Okay, so we get RAX, positive, right, equals 0. There's no x forces. Step 2, sum of the forces in the y direction has to equal 0. Start from left to right like you read in the book. Reaction at point A in the y direction, minus 8,000 pounds, minus 7,200 pounds, minus 3,500 pounds, plus RBY, reaction at point B in the y direction, has to equal 0. Two variables, can't solve it. So I'm going to reduce it though. So RAY plus RBY, I'm going to add these up and move them to the other side of the equation. 8,000 plus 7,200 plus 3,500 equals 18,700. Okay? All right, so now I need my third equation. Okay? Step 3, sum of the moments. I'm going to use point A equals 0. What you want to do is you want to find a point that gets rid of the most unknowns. So I'm going to use point A. RAY, the line of action goes through the point of rotation, so that's 0, so I can ignore it. So all these, this 8,000, 7,200, and 3,500 pound force, they're going clockwise, so they're negative, and the RBY is positive because it's going counterclockwise. All right, so, whoops. Where was I? Here I am. Let's unzoom this somehow. Can I? I guess it doesn't matter. All right. So we're rotating about. So A right here. What do I want to do here? There we go. That's what I want because I like switching back and forth. Okay. So minus 8,000 force times the distance times 3 feet. Okay. Minus 7,200. So the minus is the rotation. 7,200 is going clockwise around point A. So what's my distance? So I know it's 6 feet plus 6 feet is 12. Okay. Times 12. Okay. Minus 3,500. All right. So we have 6 plus 12 is 18. Plus 4 is 22. Okay. And then RBY is going counterclockwise. So plus RBY times the total length of 24 feet equals 0. Now I can solve for RBY. So if you do a bunch of algebra, okay, 8,000 times 3,200 times 12 plus 3,500 times 22 equals, right, that's a negative 187,400. Now I slide that to the other side of the equation, that turns positive, and then I divide that whole thing by 24, and I get 7,808. Oops, 7,808. Well, if you want 0.333 repeating, and that is foot-pounds. Okay, I end up with a positive number, RBY, so I assume my sense was correct. Okay? So that's one of the answers I'm looking for. These problems basically want to solve for reactions or solve for a tension in a cable. Okay, so now I know that. Can I substitute in now? Can I substitute into the sum of the forces in the y direction? Absolutely. I know RBY. So I know So I'm just going to do the algebra right away. 18,700 pounds. Whoa, that's not right. Right here. 18,700 minus, right, RBY. I'm going to subtract it to get it over here. 7808.3 equals RAY. Okay? All right? Then that will be 18,700 minus 7808.3. 10,891.7 pounds equals RAY. All right, so RAY equals 10,891.7. This equals 7808.3. Okay, and RAX equals 0. Okay, so now all my answers became positive because I did my algebra. Remember, just make sure you follow algebra rules correctly. If it's a negative, it's a negative. That means I got to switch the sign. You got to switch the sense. You correct the free body diagram, and then you check for equilibrium. Okay? So let's check for equilibrium. I'm going to add a slide. Okay? Just going to cut this. All right. Check for equilibrium. Sum of the forces in the x direction has to equal 0. Okay? If I go back, what do I have? RAX equals 0. Check. Sum of the forces in the y direction equals 0. Okay? All right, so RAY, so I start from upright, 10,891.7. 10,891.7. Okay? Minus 8,000, minus 7,200, minus 3,500. Minus 7,200, minus 3,500. Plus RBY, correct? Which was 7,808.3 pounds. 7,808.3 has to equal 0, or approximately 20, depending on the rounding. 7,808.3. Okay? All right. So 10,891.7 minus 8,000 minus 7,200 minus 3,500 plus 7,808.3. Did I miss something here? Let me double check. I don't get 0. Minus 8 minus 72. All right. That's the second. So 10,891.7 minus 8,000 minus 7,200 minus 3,500. There it is. Okay, plus, I must have punched a number wrong in my calculator. 08.3, and I get 0. So yes, that equals 0. I'm on the right track. Now, the really good final check is sum of the moments about point B. Now, it's very important that you use a different point. Before I used point A. Now I want to use point B. Okay, because no matter where I rotate about, it should equal 0. This would be the check to make sure I did all my moments correct. This is your true check right here. This is the biggie. So if you get 0 or really close to 0, you know you did the problem right. Okay, so I'm going to sum all the moments about point B. So RAY is going clockwise, so that's a negative. So minus 10,891.7 times 24 feet, because my distance, my perpendicular distance is 24 feet. Okay, now these are all positive here. Okay, so we got plus, positive rotation equals plus 8,000 times, I'm going to put this, plus 7,200 times the distance, plus 3,500 times a distance. Okay, so let's figure out those distances. All right, 8,002 point B. So we have 3 plus 12 is 15, plus 4 is 19, plus 2 is 21 feet. So this is 21 feet, 7,200 pound. Remember, it's the point load, so it's 6 feet from here to here, because it's in the middle. So 6 plus 4 is 10, plus 2 is 12. So I got 12. Okay, R, and then the 3,500 is 2. Okay, then the last one is, what do we have? We have RBY. Now, that line of action goes through the point of rotation, so don't we have anything? RAX, the line of action goes through the point of rotation. We have no point of or we have no perpendicular distance. That means it's 0, even though this answer is 0 anyway. Okay, so when I do this math, this should approximately equal 0 if I put everything down right. Okay, so we go 0.7 times 24. Okay, so we take that answer and turn that into a negative. Oops. All right. 10,891.7 negative times 24. Oops. 10,891.7. 10,891.7 negative times 24. All right, just give me a negative. All right. 0.7 times 24. Right? 21 1,700 times 12 minus 3,500 times 2. And I get 0.8. 0.8. Really close to 1. So we're good. All right. So if you know if this is wrong, you'll get a really high number. You may get a whole number like a 1 or a 2, because it depends on this rounding right here. Okay. So this tells you that I did everything right. Okay. So I just did example 3. Okay, I solved for RAY, I solved for RBY, so those are the loads on top of the wall, and RAX, so this is, all right, so that's what that's problems of equilibrium. So this distributed load could be like a tank or something, so what you do is you turn it into a point load, so we can solve moments, let's figure out what the weight on the each of these walls will have to be in a building, okay? All right, example 4. Okay, example 4. So I'm going to go ahead and add another slide right away, because I know I'll need more room to write. It seems to be working out. All right, so I want to solve the reactions at point A and point B. Point A is a pin, point B is a roller. Remember, there's 3 equations of equilibrium. So these could be drilled, piered foundations, This looks like a transmission line, okay? So the way I want to know the forces, basically, due to principle of transmissibility, by solving these reactions, I can figure out what's my load on top of these foundations, okay? So, step one, free body diagram. The reaction at point A in the y direction, that's a pin. All right. The reaction at point A in the x direction, this is a roller. Okay. Reaction at point B in the y direction. Three equations of equilibrium, three unknowns. Okay, that was step one, free body diagram. Step two, all forces are turned into x and y components, and all distributed loads turn into point loads. We don't have any, so we're good. Step three, we can now go into our equations. Sum of the forces in the x direction equals 0. Okay, all right, so with that, get comfortable here. All right, so we have RAX, the sense is pointing to the right, so it's positive. RAX minus, I have a 4-kip horizontal force, minus 4 kips equals 0. So I know RAX equals 4 kips. Okay, next equation. Sum of the forces in the y direction has to equal 0. Okay, so we have, I'm going to go from left to right, we have minus 10 kips plus RAY plus RBY, reaction at point B in the y direction, minus 15 kips equals 0. So when I reduce that, I know RAY plus RBY has to equal, and I move 25 kips if I just do algebra. Okay? I don't know RAY or RBY. Sum of the moments for point A equals 0. So it doesn't matter which point. I can use point A or point B. When I check my equilibrium, I use the other point. I could go up here and use it, as long as I know distances. All right, so RAX and RAY, the lines of action go through the point of rotation, so those 0 because there's no perpendicular distance. So I just got rid of two unknowns. Okay, so 10 kips is going, right? It's going counterclockwise around point A, so it's positive 10 kips. So you notice sometimes I put my units in, sometimes I don't. I don't care as long as you get the final units at the end. All right, that's the key. Okay, 10 kips. Okay, it's a vertical force. I need a horizontal distance. 4 at 16 feet. So that means each of these bays is 16 feet. 1, 2, 3, 4. So I got to get to point A. So from here to here, my line of action, perpendicular distance to my point of rotation. Even though it's way down there, it's still perpendicular. It doesn't matter. It's perpendicular. So 16 plus 16 is 32 feet. Okay. Now I'm at RAY, RAX. Now I'm at RBY. That is going counterclockwise also, so that's plus RBY, okay, times 16 feet, right? Perpendicular distance. Okay. So counterclockwise, counterclockwise. 15 kips. Okay. 15 kips is going what? Clockwise. So that's minus 15 kips. Whoops, I didn't want to put parentheses around that whole thing. Erase that. Minus 15 kips. There we go. Times perpendicular distance to point A is 32 feet. All the way to there. That's my perpendicular distance. So that's 32 feet. Okay. All right, now don't forget about the 4 kips. 4 kips is also going counterclockwise around point A, so that's a positive rotation. Plus 4 kips times, what's my perpendicular distance? That's 30 feet. So I just want to review. 10 kips, counterclockwise, positive, times 32. RBY, okay, is going, because it's pushing up, right? Attach a string to it. Counterclockwise, positive, times 16. 15 kips is going clockwise, so that's minus, negative rotation, times 32 feet and 4 kips, right? It's going with my, I'm looking at my sense, and it is going counterclockwise around A, so that's positive, and my perpendicular distance is 30 feet, and that has to equal 0, and I can solve for RCY. Okay? So 10 times 32 minus 15 times 32 plus 4 times 30 equals, so I get a negative 40 kip feet, right? Okay, and I move that over to the left side of the equation. It turns into positive, and I divide that whole thing by 16, and I get 2.5 kips equals RBY. That's going to double check my math. This is where you're going to mess up, because if you have a negative sign, that means I assume my sense was wrong. 10 times 32 minus 15 times 32 plus 4 times 30. Whoa. 10 times 32 minus 15 times 32 plus 4 times 30 is 40. There we go. Divided by 16, right? We're doing the algebra. It comes to a negative 40. That goes positive when I move it to the other side of the equation. Divided by 16, and I get 2.5 kips. So this equals 2.5 kips. Okay? All right. Now, if I'm going to do substitution. Okay, so what am I going to substitute? I'm going to substitute RBY into this equation. Okay? So, this for steps 1, 2, 3. First step, right over here, free body diagram, X and Y, and point loads. Okay, going to step 4. Substitution. So RAY plus 2.5 kips. That's what RBY equals, right? Equals 25 kips. So that means RAY equals 17.5 kips. 25 minus 2.5. 22. Oh, that was wrong. 22.5. I don't know where I was getting that from. All right. 22.5 kips. Okay. 22.5 kips. This is 4 kips. All my answers became positive. I do not have to correct my free body diagram. Okay? So that means now I can check equilibrium. Sum of the forces in the x direction equals 0. My RAX is 4.5. We believe. That's 4, I'm sorry. 4 kips minus the 4 kip load equals 0. Check. Sum of the forces in the y direction have to equal 0. Okay. So I have minus 10 kips. I can, okay. Plus 22.5 kips. Plus 2.5 kips. Okay. Minus, what is that? over there. 10, can't see it. Minus 15. Minus 15 kips equals 0, and it does. 25 and 25, okay? Sum of the moments about point B, ST equals 0. Another point of rotation, right? Point B, okay. REX still, the line of action still runs through the point of rotation, so we can get rid of that one in our moment equation. 10 kips is now going counterclockwise, so that's positive. 10 times 16 times 3, right? Because my perpendicular distance, so 32 plus 16 is 48. So again, it's going counterclockwise, so it's positive. So 10 times 48, 10 kips times 48 feet. Okay, all right. Okay, RAY is going clockwise around point B, so that's a negative 22.5 times 16. It's a negative rotation, 22.5 kips times 16 feet. You know, sometimes I put it in there. Okay, so I got this. RAY, RBY is going right through the point of rotation. Now I got 15 kips is going clockwise. Right, look at the sense. I'm going clockwise, so 15 times 16 minus 15 kips times 16 feet. Okay, and then the last one is the 4 kips. That is going counterclockwise, so that's a positive times 30 feet. Plus 4 kips times 30 feet. Should approximately equal 0. And let's see if that does. So 10 times 48 minus 22.5 times 16 minus 15 times 16 plus 4 times 30. And I actually get 0. Check. Bada boom, bada bing. We just solved this reactions. Okay. So reaction. So the ground. So in this case, in a transmission line, the ground is actually holding up this load. So if I look here, if I draw the free body diagram here, so at this point, there is a 22.5 kip load pushing down in the ground. At this point, there is a 2.5 kip pushing down. So as you can tell, there's more load on this side, so it wants to tip over this way. Okay, and then there's a horizontal force that the shafts have to hold to resist the horizontal load, because that could be a wind load. Okay, so you see, notice what I did. I went from the reaction to the structure. Say I moved structure, so my line of actions are the same, my senses are opposite, my magnitudes are the same, but the point of applications are the same. Okay, so that's what I would use. These numbers right here, 2.5, 4, and the 22.5, what I would use to do my foundation design from the loads from the transmission line down into the ground. Okay, so that was that guy. Okay, one more example, and we should be done. I wanted to go back to ASTM C78, breaking a beam. Okay, so remember when we broke a beam, it's called number to third point loading. So remember, there's this little bracket here, right here, right? Would you agree that this would be a reaction force? And there's another bracket here. Okay, so I'm going to call this RA, RB, right? Now the machine is pushing down on it, correct? In the middle of this. Okay, so say there's 100,000 pounds pushing down on it. That's what it broke at, just for an example. By knowing the distance, so if this was in a centroid, which it is of these two blocks, we know we can assume that right here, half of it was here. That's why it's so important that we make sure our beams are centered where they need to be in this contraption. 50,000 pounds, okay? So I take this away, so that's the load from the machine pushing down. Now I transferred 50,000 pounds here, 50,000 pounds here, okay? I know my distances. Can I calculate the moments? Absolutely. So I equals BD squared. That's modulus of rupture. P, that load times L length. So they basically, what they do is they derive this formula to calculate the modulus of rupture, because remember, this beam is doing what? Remember, it's bending, and then we have a B, okay? This is a B, and this is a D. So anyway, this is derived from using moments. So I can figure out this force from that load pushing down, which is 50,000. We know a distance, so I can create a moment here. I create a moment here. I can calculate these reaction forces, okay, times, and then we can figure out the stress in there, and that's how we calculate the modulus of rupture. So I just wanted to bring this back to you. So where are these formulas coming from? It starts right here, doing moment equations. So, okay, because this is a point load, this is a point load, right? Because those two top third points, and then that we can calculate equivalent into a reaction load. Okay, so that's kind of where that all comes from. I just wanted to give you that just to bring you back cement and eggs. Okay, so with that, here's your homework. Okay, read chapter 4. Here's your homework problems. Reach out to me if you have questions. And hopefully you heard me this whole thing, otherwise I got to do the whole thing all over again. So thank you for your attention.